Though in this video we're going to be talking about batteries, fuel cells, and corrosion. So this is our next learning objective, learning objectives 2 and 3. So let's look at what makes something a battery. So I've talked about already how a battery is a galvanic cell, or they're formed from galvanic or voltaic cells. To be a battery specifically, we have to have 2 or more voltaic cells connected in a series. Okay, so the voltage is produced by a redox reaction within a cell, in the cell itself. So we've talked about the fact that galvanic cells produce electrical energy through chemical energy. So this is a chemical reaction. Chemical energy being converted into electrical energy. Okay. The electrodes themselves are going to be immersed in electrolyte solution, and we force the electrical charge to separate in the form of ions and free electrons. Okay. Batteries can be either primary, which are non-rechargeable, or secondary, which are rechargeable. And then our secondary are rechargeable, so the redox reaction can be reversed. And that redox reaction is reversed through the introduction of electrical energy. Okay, we're just going to talk about a couple of different batteries. First one is a lead-acid battery. That's the type of battery used in cars. And here we have 6 voltaic cells in series. Each one produces 2 volts of energy. Okay, so in a lead-acid battery, lead solid and lead oxide are the electrodes. So kind of weird electrodes in this case. And our cathode can be written as lead oxide, reacts with HSO4 minus, which is why it's a lead acid battery, right? Plus 3H plus 2 electrons, produce lead sulfate and water. So this is why you don't want to get battery. So battery acid, when they talk about battery acid, they're actually talking about acid like we know. Our anode is a little bit simpler. We have a lead solid plus HSO4 minus, producing lead sulfate, H plus ions, and 2 electrons. So if we look, our overall, we're going to have lead oxide plus lead solid plus 2 HSO4 minus plus 2H plus goes to 2PbSO4 plus 2 waters. Here we have lead 2 plus going or lead going to lead 2 plus in this case. So when we figure out our E cell here, we're going to do our reduction of our cathode. So this one right here, excuse me. So we're going from lead 4 to lead 2, and that has a reduction potential of 1.69 volts. And then in our anode, we have lead solid going to lead 2, and that oxidation has a value of 0.36 volts, overall giving us a cell potential of 2.05 volts. So that is the 2 volts we see here, and each one of those voltaic cells in series will produce those, so we have 12 volts of energy in a typical lead acid battery. As a note, these are rechargeable, so you can recharge this, and which should be obvious since these are what are used in cars. But as we drive, we recharge that, forcing the reaction to go in the opposite direction. Next battery I want to look at is a lithium-ion battery. This is another rechargeable battery. And here we have lithium ions flowing between the cathode and the anode, which we can see right here. And during the charge and discharge processes, lithium ions are inserted or extracted from the interstitial spaces between the layers in our anode and our cathode. So the interstitial space is a empty space in between the layers. Okay, so the ions are going between the anode and the cathode. So at our cathode, we have a cobalt oxide species. That reacts with the lithium ions. To produce this lithium species. And then at the anode, we've got a lithium species. That reacts with our graphite layers to produce lithium ions. And our overall reaction is written as follows. Like so. As we can see here, our overall cell potential here is 3.7 volts, so a fairly large voltage. Last thing I want to talk about as far as our different types of batteries is a fuel cell. It is an electrochemical device that converts hydrogen and oxygen into water, producing electricity on the way. And this does not need to be recharged like most batteries, so as long as we continuously supply the hydrogen and oxygen, the fuel cell will never die. So it's not something that you have to reverse and then go back forward. Okay, so here at our cathode we have O2 gas reacting with H plus ions to produce water. And then at our anode we have H plus gas producing those H plus ions like so. So you're basically supplying H2 and O2 here, and you get O2 gas plus 2H2 gas gives you 2H2O liquid. So you can see that here. Introduction of H2 and O2, and it has a cell potential of 1.23 volts. Last thing I want to talk about in this video is the idea of corrosion and preventing corrosion. So corrosion itself is oxidation. It's just a fancy way of naming it. And the most common oxidation or corrosion process that we are probably familiar with is rusting, which is going from metallic iron into iron 2 oxide and then iron 3 oxide. So like I said, we go from iron solid to iron 2+, to iron 3+. And in this process, so here's the first one, right here. And then there's iron going to iron oxide, or iron 3 oxide. So this process, all included, requires both oxygen and water. For it to occur. And basically what happens is the iron acts as the anode, and the O2 is reduced, acting as the cathode. So the problem is that it's basically being oxidized because it's acting as an anode. If there's a species that can be added to protect it, then we can cause that corrosion not to occur, and we call this process cathodic protection. So we make the metal that we're trying to protect the cathode instead of the anode. So we will protect the metal by making it a cathode. If you have a metal, it cannot be any further reduced. So making it the cathode is going to stay in its normal state. So you can do this, you can make your metal a cathode by adding a material that has a higher oxidation potential, something that is easier to oxidize. Zinc is used a lot of times for this, so if you hear of a zinc coating to protect a metal, an iron species, the zinc now will act as the anode, going from zinc to zinc 2+, and then the iron is the cathode and it doesn't do anything. So it is not oxidized. So that is how we protect things from oxidation. Okay, that's everything. We have one more video, and we're done with this this whole class. Bye, y'all.